So essentially what we're doing right here, essentially the plan right here, right, is to integrate this. And so you might say, okay, how do we integrate this? Well, you look at what we're integrating, right? And you notice two things, right? There's an x squared function right here. And there's a trigonometric function right there, x squared times sine of 4x. Okay? So very big thing to notice right here. Product of two functions. Almost all the time when you have a product of two functions like this, it's going to mean integration by parts, okay? Because when we differentiate products, we use the product rule, okay? But when we integrate products, the I don't want to say opposite, the inverse, if you will, of the product rule is integration by parts, okay? So that's what we do here. Whenever you do integration by parts, right, you go off to the side and you say, okay, we need to find a u, we need to find a dv, and then we'll calculate our du and our v. And I probably didn't give myself enough space to write here. Okay, so u, right? U is the thing that we want to differentiate easily. dv is the thing that we can integrate easily. We need to figure out, okay, which one of these things, which one of these things is easier to differentiate, and which one of these things is easier to integrate? Now, you, of course, being the astute and awesome calculus students that you are, you may realize, Jason, Melyn, they're both easy to differentiate. They're both easy to integrate. Well, it's your lucky day, right? Or is it? Think about this, right? So in this case, this is a maybe more interesting case of integration by parts. Differentiating the x squared is going to make it a 2x. Anti-differentiating the x squared is going to make it a x cubed over 3. Smaller powers, better powers. Okay? So that's what we're going to do over here. It's easy to, if we differentiate x squared, we get something really nice. Oops, not that. We get 2x dx. And yeah, I didn't give myself enough space. And then integrating, all right, and then our dv is going to be what's left over. Sine of 4x dx. And so, of course, the v, we need a little bit of extra room, okay, is the antiderivative of that. Usually to take the antiderivative of things like this, we'll use a u substitution, but we're far enough into the semester that you don't need a u substitution to do this. It's just going to be 1/4. Antiderivative of sine is cosine, negative cosine. All right, so there's a negative out in front right there. All right, hey Dork, you ready for some math? All right, so now we've got some good stuff right here, right? Did I switch to black? Yeah, good. We have our u, we have our v, we have our dv, we've got our du, right? So what we're going to do right here is just use the formula. And a lot of times, and again, you're probably kind of past this. You're probably past this point by this. You're probably past this by this point, right? But when you're learning formulas, let's say you don't, hypothetically, let's say you don't remember integration by parts. Hypothetically, right? If you don't remember integration by parts, one of the best ways to learn a formula is to write it down when you're using it, okay? Don't try to use it and remember it at the same time. Let's just write it out. So it's going to be equal to uv. Hold on. I'm trying to figure out how to make this work with this glove. It's going to be uv minus the integral of v du, okay? So, gosh darn it. There's a way for me to make this work with this glove, but it's been a little difficult every once in a while. And now, once you write the formula down like that, all you have to do is plug things in, right? So let's try to use all the colors of the rainbow. What have we got over here? Well, u, whoop, is right there. V, we already found that. Whoop. You just plug it in, just replace it, okay? So we go right here. What is u? We said u is x squared. All right. What is v? We said that was negative 1/4 cosine of 4x. All right. Next, minus the integral of v, which again we just said was negative 1/4. Let's take the negative out in front, turn it into a positive. Take the 1/4 out in front as well. Cosine of 4x times du. I'm pointing with my finger. You can't see the finger. Maybe I need to point with a different method. Well, du we said was over here on the, right there, was 2x dx. Okay? So we did an integration by parts. And you say, hooray! We successfully did an integration by parts. We're done. Well, you're right on the hooray part. The you're done part is not so right. Because look, what do we got? Right here? Of course, we can deal with that. No problem. Okay? But this, I don't know how to integrate that. Or do I? What do we have over here? We have cosine of 4x. And we have 2x. Oh! You get to use integration by parts again. 2 for 1 on this problem. Example 1, more like example 2 for 1. Okay, so you gotta step back and do the whole thing again. All right, so let's get into that. So again, the first thing we can just simplify real quick is just negative 1/4 x squared times the cosine of 4x. All right, and that's just gonna sit there for a while. All right. Then again, we have to go over here and do integration by parts twice. Or a second time. We already did it once. All right, integration by parts. Blue for integration by parts. Why not? Definitely running out of room again, so I'm going to make a little room over here. Again, just like before, if you ever do integration by parts and you have some sort of monomial, x squared, x cubed, x to the 4th, x, that's almost always, not always, but almost always going to be your u. Okay, because they're very nice to differentiate. When you differentiate a monomial, you get a smaller power monomial. Okay, so we got u is just equal to 2. Well, if we did this a little smarter, right, we would have taken that 2 and brought it out in front. But, well, we're already here. It doesn't matter. We're fine to deal with this. The u is just going to be 2x. Du is going to be the derivative, which is just 2 dx. Right? dv is the other thing, the cosine of 4x dx. And so v is going to be the antiderivative, which will also not have enough room. It's going to be, again, negative 1/4. Oops, positive this time. Think. Antiderivative of cosine is positive sine, so it's going to be positive 1/4 sine of 4x, like so. Okay, so just like before, we have this formula. You can rewrite the formula if you want, but you don't have to. You know, it's right there. It's writing the formula is just to help you learn it and to help you plug things in. But since we already have it so close, it shouldn't be too big of an issue. Also, it's right here. So it's already right here. I mean, what I'm going to do is to give myself enough room. I'm actually going to add on to this line by writing it down here. Okay. So this is originally, and now we need a plus uv. So that's u times v over here on the right, which is going to be 2x times 1/4 sine of 4x minus the integral of v du. Okay. Minus the integral of v du is these two things multiplied by each other in the integrand. Okay. So we get the integral of v, which is 1/4 sine of 4x times du, which is 2 dx. Now there's one thing missing here. A mistake that's very easy to make. And if I'm perfectly honest with you guys, I actually did make the mistake. Does anyone see what the mistake is? It's easy to fix, but there is a mistake. Going from this line to this line. So what we have here is, of course, this first piece we just rewrote. All right, and that's okay. But notice when we use integration by parts is the uv minus v du, which is right here. This is the integral right here. Unfortunately, there's a coefficient in front of the integral. We haven't written the coefficient here. So watch out for that. So in this integral, it should be plus 1/4. Let me erase this plus sign and give ourselves a little bit more room. Plus 1/4 times the integral, which is this whole thing right there. Okay. And now it's right. And now we're almost done. In the next step, well, the next step, let's simplify. In the step after that, we're going to be done integrating. Okay. And then it'll just be simplifying. But most of what you're done with integration by parts at the very least. Okay, so the first thing, right, this thing right here is already simplified. So let's just copy that down again. Okay, negative 1/4 x squared cosine of 4x. All right, and now what do we have next? You can either choose to distribute that 1/4 now or distribute it later. I prefer distributing it now, to be honest, but it's up to you. Okay. So you distribute the 1/4. Let me write that we're distributing it to the first term, distributing it to the second term. And be very careful with your algebra, right? Distributing is only across addition and subtraction, okay? So what we are not doing is saying, oh, the 1/4 goes to the 2x and the 1/4 goes inside here. No, no, no. Those things are multiplied by each other. So the 1/4 only goes into one of those places. Algebra is going to get you most of your mistakes. If you feel like, if you feel not completely drowning, most of your mistakes are going to be algebra mistakes, especially in these long problems like this. Okay. So again, what do you got? We got negative. We got that first term copied over. Now we're distributing that second integral 1/4. What do we have? Right. We have 1/4 times 2 times a 4th. It's going to be 1/16 times 2 is 1/8. That's going to be our first term. 1/8. And then only an x, and then sine of 4x. Okay. And now distributing to the second term, that second orange. Is it red or orange? It looks orange to me. I think what I'm seeing might not be what you're seeing. I think you're seeing the same thing as I do. I think you're seeing orange. Anyway, the second thing, well, we've got, again, a 1/4, a 1/4, and a 2. Same coefficients. That's interesting that we have the same coefficients. Maybe it's not super interesting. So it should be, again, a minus 1/8 times the integral of sine of 4x dx. All right. So now we have 3 terms. One term has an x squared. One term has an x. And one term has no x's. And that should be sort of expected because of how the integration by parts works. We keep reducing the power of the x squared. We keep deriving the x squared, derivatating. I'm going to make up that word, okay? The x squared over and over and over again, okay? So that's why we have the 3 different powers right there, kind of like a quadratic. Anyway, so this fully simplified, this fully simplified. The only thing we have to do is deal with this last guy over here, okay? So what have we got here? Just a simple antiderivative. We've essentially done that antiderivative a lot before. So we got, wait, hold on. I wouldn't do this during an actual lecture, or maybe I would just to be annoying. Watch this. Wait, hold on. How do I do this? Oh, I thought I could do this. I thought I could copy and paste the line, but I think it's not so easy with this app maybe. Anyway, so we have negative 1/4 squared times the cosine of 4x plus 1/8 times x sine of 4x minus this last integral. What's the antiderivative of sine? We already did this, right? We already did this right here. Antiderivative of sine of 4x. It was negative 1/4 times cosine of 4x. We already have a 1/8 in front. So 1/8 times a quarter is 1/32. And our derivative of sine is cosine 4x plus c, because we're doing an indefinite integral. Don't forget the plus c's. Also, I have to remember that you guys can't actually see as far down as I can. Like the edge of your screen is like right. All right, never mind. It's hard to do. I have to be careful. Okay, so this should be our answer. And be very careful. Be very careful, because I know people love simplifying. I know you're gonna do this problem. You're gonna say, I don't want to be done. This problem is so sweet and juicy. I want to do another step. But don't do another step. You might say, oh, we got a cosine and a cosine. Let's combine the cosines. These are not like terms though, right? This term has an x squared. This term doesn't have any x's. Well, not in front of the cosine anyway. So this is actually going to be our final answer. All right. We'll box this with green. We haven't used green yet. Oh, I was never very good at kindergarten. That box. It's not so good. All right. We're not erasing it though. We'll take that. And let's say, hypothetically, let's say you're taking an exam, hypothetically. And let's say you're taking an exam, and on the exam, you have extra time left. Because your math professor doesn't want you to be rushed. So he makes a short exam. You know what you could do? You could check your answer. All right. Oh, yeah, it's negative. Negative should cancel. Good catch. Although, maybe I should shame you for catching that. Because if you didn't catch it, we'd catch it when we checked our answer. How do you check your answer for an antiderivative? You just differentiate your answer, and it should match up with the original problem. Okay? So, this is where I'm really not happy. There's got to be a better way of dealing with this, because I would really like to not have to remember this, copy it over. I think there's a super easy way to do that. This, by the way, is why I'm practicing right now on stream. So when I'm making my videos, I don't run into this issue. So what I can do is I can make a new page, but then I have to go back to the old page. I want to remember it. Maybe it's okay. So let's check our answer, okay? Yeah, it's when I'm writing at the top left that I really have to be careful with this glove. All right, what is the derivative of our answer? What was our answer? Negative 1/4 x squared cosine of 4x. Oh no. Plus 1/8 x sine of 4x. And then it was a plus, right? Plus 1/32 cosine of 4x. If you wanted to, you could check your answer right there. All right. So we're going to check our answer. And in checking our answer, right, it's going to be a little annoying, because what do we have? The derivative of three things added together. We can just take the derivative of these three things individually. But notice the derivative of this requires the product rule. Requires a product rule. This requires a product rule too. So this is going to be a little long. It's going to be a little messy. But say you have an extra 5 minutes on your test. It's always worth it to do. Okay? Because I said, what is the most common error you're going to make? Algebra errors. I've already made 2 errors, one of which I caught, the other which I didn't catch, right? I've already made 2 errors. And I probably am more practiced at this than most of you. So you're going to make errors. It's going to happen. And there's nothing to beat yourself up about it. People make mistakes. That's why we check our answers. Okay? So what we got here? The derivative of the first thing. Let's just not worry about the negative 1/4. We can keep that in front. And then derivative of the first, which is 2x, times the second, cosine of 4x. plus the first, x squared, times the derivative of the second, which is negative 4 sine of 4x. All right, and I guess we have 3 parentheses here. Okay, right, because the derivative of cosine is negative sine. And then we have to use the chain rule within the product rule and multiply by that 4. Okay? That's the first term. Next, let's move on to the second term. Differentiate the second term. Product rule again. Okay, so we have a 1/8 out in front times the derivative of the first, which is 1, times the second, sine of 4x, plus the first, which is x, times the derivative of the second, which is 4 cosine of 4x. Again, requiring the chain rule. All right, and now we got the last term. No product rule necessary here. That's kind of nice. So we just get minus. A 4 comes out in front because of the chain rule, so we get 4/32, which is 1/8, times the sine 4x. And you might say, wait a minute, hold on, Jason. You just said this is what we should get back. Well, the integrand, right? Not actually the integral. You said this is what we should expect. Well, if I'm really being pedantic, this is what we should expect. Okay, that's not what we got. It doesn't look like that. Well, you're gonna have to simplify, of course. All right, so does anything cancel? Hopefully. hopefully. So what do we got here? Well, before we cancel, we have to simplify each term individually. So let's just simplify it real quick, right? Let's distribute that negative a fourth. Negative a fourth times 2 is negative a half. And then there's x cosine of 4x. That's that. And then distribute the negative fourth to this part, right? Negative fourth times negative 4 is positive 1 plus x squared sine of 4x. That's our first term. Now distribute the second one, right? That's going to be plus 1/8 sine of 4x plus 1/8 times 4 is 1/2. 1/2 x cosine of 4x. All right. And then the last term, no distributing necessary, minus 1/8 sine of 4x. And this is where things get really exciting or really panicky. Okay? If you did things right, this is exciting. If you goofed, this is where you start panicking. But the panic is okay, right? Because if you find out that you have the wrong answer, of course it always sucks to get the wrong answer, right? But it means that you know you have the right answer and you might have time to fix it. Okay, so let's look. Hopefully we have things. Let's look at like terms. Wait a minute. What's our first term? Negative 1/2 x cosine of 4x. Over here we have a positive 1/2 x cosine of 4x. Whoa! Isn't that exciting? Those cancel. They add to 0. What else do we have? An x squared term. We have another x. No, there's no more x squared terms. So this thing right here is stuck by itself. But look at these two like terms. Plus 1/8 sine of 4x minus 1/8 sine of 4x. Those cancel too. What are we left with? We are left with exactly what we wanted, right? Because this thing right here, the original integrand. This is like calculus 2. Some people take calculus 2 in college. Some people take it in high school. I took it in college. So this is what we wanted. So give yourself a little happy face.
Where are your friends?
All right. Hey, thanks Restless Soul for the resub. I appreciate it.
Thanks for being awesome.
Sine and cosine are trigonometric functions. I think in my entire year, I think in high school, only one student in my level took this class in high school. So yeah, most people will do this in college, but I don't know how it is outside the state. That made you climax? That's the reaction I'm looking for in my It's probably not an appropriate thing to say in a classroom environment. I admire your enthusiasm. Okay. So yeah, that's kind of what we got right there. So let's look at what we did, right? The actual integral was kind of messy, but it took up one screen here. Checking our answer was also another total screen. Okay, so it'll take some time. But if I didn't catch sign error over here, remember I made a sign error right there? If I didn't catch it right there, I would have noticed it right here because these things wouldn't cancel anymore. Okay, this cancellation would not have happened anymore. So always good to check your answer whenever you have time. Sine and cosine are just like a function, just like the square root function, right? It just does stuff. So like sine and cosine, it's easy to see what sine and cosine do. Well, not easy. It's easier to see what sine and cosine do if you view them graphically. And I think if I wanted to, I could do that. Right? So if we look at a, we look at like a graph, sine and cosine. Use your imagination. Essentially do this. Forever. Endless waves. Okay, and both sine and cosine behave kind of like this. All right. And as a reminder, something that's a very good tool for you this semester, if you were hypothetically my students, and even if you weren't hypothetically my students, say you were random Twitch viewers, something that's very, very helpful in visualizing math is like, say you had questions. What you could do, there's this very great website, desmos.com. Hold on. I may have to fix this. Oh, the cropping affects it in both scenes. I thought the cropping was unique. But anyway, you can visualize it right here. Yeah, you guys can't see it very well here. Bring this over to you a little bit. All right, what we sort of have right here is you can type in the equation here, just y equals sine x. You can really visualize it this way. Okay. And for anyone who's doing any sort of mathematics, I would highly recommend using this website if you're ever trying to visualize functions or graphs. It's going to be very, very useful. Okay. Anyway, so that was our first integral. We can do another integral. That was number 412. And you might think, whoa, Jason, you assigned too many homework problems. First off, most of this is optional. Second off, in this textbook, this is a free textbook, openstacks.org. In this textbook, it doesn't reset the numbers every section. It resets the numbers every chapter. Okay, so this is the chapter 3 review. So it's at the very end of chapter 3, which means in the entirety of chapter 3, there's 400 and whatever problems. Okay. You taking trig this semester? Oh, I just taught trig in the spring. I taught trig on Twitch. That would have been perfect. Yeah, you can ask questions in the Discord for sure. Every once in a while, go ahead and ask questions during stream too. Trigonometric substitution. Oh, that one looks fun. You guys want to do a trig sub? Yeah, I use open educational resources whenever possible. I think buying textbooks is stupid. All right, trig sub, here we go. All right, so what have we got here? Ow, I just dropped my pen. It was kind of heavy. All right, so what we have is, I'm gonna write down the problem, but I need to see the problem, so give me a second. This is gonna be example 2. All right, so we got the antiderivative of 1 divided by x squared. I'm trying to, hold on. Every once in a while, it lets me rest my wrist on the tablet, and every once in a while, it gets really grumpy. I'm trying to figure out why it does one and why it does the other. Huh. And I don't know. Anyway, we'll worry about that. I'll worry about that later. Anyway, 1 divided by x squared. If I can write a 2, that would be helpful. You guys know what a 2 looks like? It doesn't look like that. That sounds about right, Jessica. I can't write a freaking 2. Anyway, 1 divided by x squared times the square root of x squared plus 16. Oh no, the 2 again. So one of the most important things to think about, not that you guys could even see the 2. One of the most important things to think about when you're looking at integrals is, because especially for the final, right? When you get to the final, I'm not going to say, hey, solve this integral with a u substitution. Hey, solve this integral with a trig substitution. Hey, I'm not going to do that, right? I'm going to say, hey, here's an integral. Get to work, all right? Those will be the exact wording on the final exam, okay? Get to work. All right, so you need to, one of the main skills that you can have when looking at these problems is to identify what method do we want to use, okay? So you should always be kind of having in your head, what are some of my options? First option, always, u substitution. Is a u substitution going to help? Okay, so if you did a u substitution over here, and again, you don't want to do a u substitution. We already spoiled it. The textbook spoiled it. But if you were doing a u substitution, you'd want to do the thing inside the square root. So you'd say, okay, u is going to be equal to x squared plus 16, and you go du equals 2x, and you're going to go, oh, wait a minute, this looks not helpful at all, right? Because you're going to get the square root of u, which is nice, but then this thing over here is going to be really obnoxious. You don't even have a du anywhere, and you're going to go, okay, back up the trolley, as Dorf likes to say, back up the trolley. We don't want to do that. U substitution is not going to be helpful here, okay? So U substitution is great first thing to check, all right? Other things are partial fractions. Integration by parts is a really big one too, because here we do have two things multiplied by each other, right? It doesn't look like it, but this is kind of 1 over x squared times the thing on the right hand side. But when you do integration by parts, you need to say, can I differentiate one of these pieces and make it easier? Can I integrate one of these pieces and make it easier? And the answer to both of those questions is definitely not. If you try to integrate, any pair of integration and differentiation here is just going to make things really ugly. If you're really creative with integration by parts, I feel integration by parts works in sometimes when you really don't want to use it, but sometimes it will still work. But you're going to get, it's hard for me to say this, right? Because I'm going to say you're going to get something way too nasty that you never want to deal with. But you might say, Jason, this was way too nasty. I never wanted to deal with this either. So I don't know if that's maybe the best indicator of what method you should be using. Okay, but as we mentioned when we introduced this stuff, the big thing you're going to want to look for trig subs is a square root of something squared plus something else squared, right? X squared is obviously x squared. 16 is 4 squared. Those are going to be the big ticket items to look out for trig subs. Okay? So in a u sub, we say let u equal this, all this stuff. But in a trig sub, it's kind of backwards. Okay? So do we want to trig sub sine, cosine, tangent, secant? What do we want to do? And the way that we can decide what we want to do is to remember the trigonometric identities. So remember the big identities that you're going to want to remember are are what's called the Pythagorean identities. So one of the big ones is sine squared of x plus cosine squared of x equals 1. That's a Pythagorean identity. And usually for purposes of this class, this is not the form you're going to want. The form you're going to want is like, I don't know, subtract sine squared x from both sides. And then you get cosine squared of x equals 1 minus sine squared of x. So this is going to be a very common one to use. So if we got, for example, on the denominator, the square root of 1 minus 9x squared, that's when you'd want to use this trig substitution. Say, okay, x is going to equal sine. Or actually what you do is 3x equals sine. Well, you have a couple options on how you do it. Okay. Then you can use this trig sub over here. All right, but that's not what we have, right? We have x squared plus 16. So it's not going to be that one. We need another option. What was the other option? The other option is, that's the sound my eraser makes when I write on a tablet. The other option is going to be that 1 plus tangent squared of x equals secant squared of x. All right. And yes, that's actually a very good point. Say you don't remember this one. Say you only remember the first identity, right? If you only remember the first identity, what was it that I wrote? Sine squared of x plus cosine squared of x equals 1. What if we divide everything by cosine squared? Divide that by cosine squared of x. Divide that by cosine squared of x. Divide that by cosine squared of x. What do we have? Sine squared over cosine squared is tangent squared of x. Cosine squared minus divided by cosine squared, this canceled to be 1. 1 divided by cosine squared is secant squared. Okay? So all you have to remember for these identities for trig subs is that first one. Sine squared plus cosine squared equals 1. And if you really want to know why it's called a trigonometric identity, if you think about trig functions in the unit circle, this is going way far back and nobody wants to hear about this, but I'm going to talk about it anyway. Right? If you go back to the unit circle, right? Unit circle is a circle of radius 1. Then at any point on that circle, you can draw a triangle. And the x component is the cosine of that angle on the triangle. And the y component is the sine of the angle on that triangle. So what is sine squared? Sine squared is y squared. What is cosine squared? That's x squared. X squared plus y squared equals the radius squared. Radius on the unit circle is 1. We get x squared plus y squared equals c squared, or r squared. Basically, a squared plus b squared is c squared. Okay, Pythagorean formula. Almost everyone. I don't care when the last time you took math was. Most people remember Pythagorean identity. Pythagorean formula. What did they even call it? It's been too long. Pythagorean theorem. Yes, a squared plus b squared is c squared. Okay, so I went on a long tangent, no pun intended, but it's still kind of funny. A long tangent about some stuff that's some context. And again, I'm going to go on another tangent because I'm not actually teaching in a class, and I can go on as many tangents as I want. And well, even in class, I go on tangents, right? This is why it's so important to have the prerequisites in your head when taking a class. I think 80% of the time I meet with a student and they say, I'm struggling. They're not struggling on the material I'm teaching. They're not struggling on trig identities. They're not struggling on trig substitutions. They're struggling with trig identities. Or maybe they're struggling with algebra or arithmetic even, right? If you forget something, it doesn't mean you're stupid. It just means it's been a long time since you learned it. And so realizing what exactly are you struggling with is really, really important, okay? And that's one of the things that you can talk to me about. And I am probably able to help you identify that and say, okay, let's review trig identities for a while, or let's review algebra for a while. And if you can get a solid grasp of those prerequisites, this integral becomes way easier because you're probably not struggling with the calculus at all. And that's why math gets harder and harder as you go on, because you forget stuff. And that's why so many people say, I'm not good at math. Some people, I'm sure, aren't good at math, but most of the people who say they're not good at math just don't remember something. And then every single class they need it. Every single class they don't learn it. So they don't know it. So they struggle with that. Okay? Anyway. Whew. Does anyone want to actually do an integral? Let's go. Okay, so this is, we can erase most of this because we only need this guy over here. Okay? That's the trig sub that we're going to use. So we want the inside, we want the radicand to look like this. So in order to excuse me, okay, in order to do that, what do we need to do? We need to say let x equal something. All right. So it's almost equal to this, but there are two problems with this. Because you say, okay, if x is tangent x, then we square it, we get tangent squared plus 16, which is very close to this. We can do a sub. There's two things wrong with this substitution. All right. The first thing wrong, and we didn't really cover it before, is that there needs to be a 4 here. Because then when we look at x squared, we'll have a 16, and then there'll be a 16 here and a 16 here, and we can factor it out, and then it'll look like this. Once we factor out a 16, there'll be a 1 there. The 1's very important. The second thing is this makes sense in computer programming, but this does not make any sense in math. Well, it does make sense, but not the sense we want it to make. Okay, this is the wrong sense. You can't do a substitution and say let x equal something with x. No, we need to use a different variable. I know people love x's. I know a lot of times you guys get rid of x's, but let's use variables. The very common variable that we use is theta. All right. So if we have x here, if we're doing a substitution, what else do we need to do? We need to deal with the dx. Okay. So how do we find the dx? We just take the differential. Okay. So on the left-hand side, we get dx. The right-hand side, we get 4 times, what's the derivative of tangent? Secant squared. Okay. Secant squared of theta, d theta. That's our dx. All right. And there's kind of two schools of thinking. And if I were teaching a class, I'd probably just choose one and go with it. But since I'm just randomly talking on Twitch, we'll speak the two ways of thinking. But one of the ways in doing like u subs, it won't actually affect the trig subs, is solving for dx. And another way of doing it is actually solving for d theta. But here we're just going to plug in the dx for the existing dx and be done with it. All right. So we finally got everything taken care of. We can do the substitution. So this is where things start getting messy. What do we got here? We just have the integral of our numerator, which is just fine. Well, let's put the dx in the numerator, okay? Dx, we said, was 4 secant squared of theta, d theta. That'll be our numerator, okay? We get 4 secant squared of theta. And we'll put the d theta at the end. All right. And then our denominator, we have x squared. Ooh, we didn't actually write what x squared was over here. Let's write it out. Let's write it out, okay? Right, if x is 4 tangent of theta, what is x squared? If x is 4 tangent of theta, then x squared is that thing squared. Right, so x squared is going to be 16 tangent squared of theta. All right, so this is optional, right? You don't have to write this down, but it can be helpful. The less you're doing in your head, it's going to take a little longer. But the mistakes are going to go down exponentially. Okay? And people, everybody, myself included, wants to save the maximum amount of time possible. Every millisecond that I'm not doing math is a win. But if your goal is to pass the class with a decent grade, take an extra millisecond, okay? So what do we got here? We got x squared, which we just found. That's 16 times tangent squared of theta times the square root of x squared, which again is still 16 tangent squared of theta. That hasn't changed. Plus 16. Okay? And that's our integral. Hold on, the integral sign got a little small. That's our integral. Whoosh. All right, still working on my penmanship with this, which is, again, the reason why we're here. But the reason why I'm here, I have no idea why any of you are here. That's another thing I don't say in my class. Why are you guys even here? All right, so now again, the whole point of these methods, integration by parts, U substitution, trig substitutions, the whole point is to make it easier. And you may say to yourself, this does not look any easier than what we started with, Jason. What are you doing? You crazy? Oh my goodness. But don't worry, it's not as bad as it looks. Again, this next step, no calculus involved. We are going back to algebra and a little bit of trigonometry. Okay, so try to remember back that far. If you struggle with the next step, it doesn't mean you suck at calculus. It means you need to refresh your algebra. You may need to refresh your trigonometry too. Okay, because again, we need to simplify this. We are not integrating this. Absolutely no way. Okay, so there's a couple things right off the bat, right? We got 4 divided by 16. Let's simplify that. 4 divided by 16 is a constant and it can come out in front. That's 1/4. Write that out in front. All right. Next, secant squared divided by tangent squared. Let's go off to the side. Let's look at that, right? That's not going to be enough room. All right. What is secant squared divided by tangent squared? Because those are trig functions. Those can be simplified pretty nicely. All right. Secant squared is 1 over cosine squared. Tangent squared is sine squared over cosine squared. There's a lot of different ways to simplify this, but one of the ways to simplify this is just multiply it by cosine squared over cosine squared. Because this is 1 over cosine. Well, 1 over cosine times cosine is just 1. Our numerator is just 1. That's nice, isn't it? This is sine over cosine. Sine over cosine times cosine. The cosines cancel. This is just, oh my word. Is it really that easy? It's really that easy. Well, it's not easy, but it's that, it looks that nice. It simplifies that well, okay? So again, the secant squared divided by tangent squared simplifies just to sine squared on the bottom. So I'm really just loving all these colors, but we need to just write this out. So what are we left with? 1/4 times the integral of 1 divided by sine squared of theta times square roots. And again, what do we want inside the square root? We want something that looks like this. We can use a trig sub or a trig identity. We already did the trig sub. But we got these pesky 16s here, right? We don't want this 16. We don't want this 16. But we specifically chose our value of x for tangent theta so that these numbers would match and we can factor them out. That's what we're going to do. Factor out the 16. And we're left with tangent squared of theta plus 1. And now the square root of two things multiplied by each other is the product of the square roots. So this becomes a square root of 16, which is just 4. But actually, we get a 4 that comes out into the front. Okay. So next step. 1/4 times a fourth is 1/16 times the integral. Oops. Don't forget the d theta. 1/16 times 1 divided by sine squared of theta times the square root of tangent squared of theta plus 1 d theta. And now we're getting a little closer, not super close. I won't lie to you, not super close, but a little closer to where we want to be. A little closer to being simplified. Because what do we got up here? Tangent squared of x plus 1 is secant squared. Which means, what do we have in here? We have tangent squared of theta plus 1. That's going to be secant squared of theta. Right there. Ah. We got some even nicer stuff. 1/16 integral of 1 divided by sine squared of theta times the square root of secant squared of theta. d theta. Oh, the square root of something squared? Ah, it's nice. By the way, another ranty side note. Square root of x squared, not actually just equal to x. Square root of x squared is equal to the absolute value of x. But usually for these sorts of problems, I'm going off the screen again. Usually for these sorts of problems, we just assume domain restrictions, okay? Because if you restrict the domain, right, if x is positive, for example, x is the same as the square root of x. X is the same as the absolute value of x. Because if you take the absolute value of a positive number, it's the same as just the number itself, okay? So usually that's kind of what's going on, right? All right. All right, grandpa's on top of this. 30 years be darned. So let's go on to the next page. We got 1/16. We're just gonna simplify this to secant of theta, assuming we have the correct domain restrictions. All right, and we're going to get that what we're dealing. Ooh, I tried to wipe something off of my screen, but yeah, you saw what happened. All right, so we have the antiderivative of 1 divided by sine squared of theta times secant theta d theta. And your heart's going to thump. I hear it thumping all the way from over here. Because we just finished the trig sub. Is this integral easy? Did everyone know this integral off the top of their head? No, of course you don't. Or maybe you do. Maybe you're a savant. Okay. When is this stuff going to be, when are you going to use calculus 2 in practical ways? You are never going to use it, Casper. Most people are never going to use this. All right. It just, you have to go into smarter professions than I'm in to use this stuff. Advanced forms of like chemistry and physics and stuff like that. Like high levels of research or mathematics or something like that. Engineers, yep. It really just depends on what you're doing. But for the general person taking a Calc 2 class, you're never going to use it. All right. And don't even get me started on why we're learning that. That is a whole rant in and of itself. You can talk to me after class if you're curious about that. So again, it's not calculus anymore. It's a trig problem. Let's simplify. What do we have here? We have a secant in the denominator. Secant's a reciprocal function. We don't want reciprocal functions in the denominator. If you ever have a secant theta in the denominator, or if you ever have a secant of theta in the denominator, I just said the same trig function twice. Or cosecant of theta in the denominator, or cotangent of theta. These are all reciprocal functions. You don't want these in the denominator. They're reciprocal functions. We can just flip them, reciprocate them, and exactly only iced coffee. Put that shit in the numerator. Yeah, there actually is a pretty nice application section in a Calc 2 class too, which is like a lot of times looking at centers of mass, a lot of pressure situations are integration. Integration, right? Remember what integration is? Integration at its heart is, hold on, I'm going to write this before I forget. Put the reciprocal function in the top. Integration at its heart is adding up an infinite number of things. Differentiation is rate of change. Integration is adding up an infinite number of things. So anytime that you're sort of adding things, that's like can be extrapolated to integration. Okay. Anyway, that can go on some other spot. So integral, we move the secant. What's the reciprocal of secant? Cosine. We get a cosine of theta on the top. We're left with sine squared of theta on the bottom, d theta. All right, and now we've done all the trig that we can do with this. All right. We've basically done all the trig that we can do with this. We could rewrite this using the Pythagorean identity. Remember, Pythagorean identity is, I erased it, sine squared plus cosine squared equals 1. So we could do that with the bottom if we wanted to. We could get everything in terms of cosine. But we have an integral. And we have sines and cosines. And if you only have a cosine on top, that should strike a bell, ring a bell even. Because what is the number one way that you want to try to integrate something? If I give you an integral, what's the first thing that you try? Integrate. The first method that you look for to integrate is a u substitution. And I claim, you don't have to believe me, but I claim that you can use a u substitution right here. Okay? Because the derivative of sine is cosine. So if we go over to the side and say, let's let u be sine squared. Not that. Let's let u be sine of theta. For u sub, what is du? Going to be cosine of theta. D theta. So notice, this is our du right here. Cosine of theta, d theta. We already have the du. And this on the bottom is just u. So that's perfect for a u substitution. All right? It's so perfect that you can't possibly complain. All right? So what are we left with? We're left with cosine of theta, d theta. We said that was just du. Sine squared. Oh, I said sine squared was u. I was wrong. Sine squared is not u. Sine of theta is u. So sine squared of theta is going to be u squared. And whoa, look at that. That's an integral that you know how to do. Okay? I can guarantee that if I were speaking to an actual Calc 2 class at this point in the semester, you know what to do. All right? So this is just the power rule. Okay? The most basic integral we did at the very beginning of the semester. All right? We're just going to power rule it up. It took 2 substitutions to get there, right? First, we did a trig sub, let x be something in terms of theta. And then we went over here and we did a u sub. It took two substitutions, but here we are. We can finally integrate. Wow, easy. Yeah. All right, so, right, it may be beneficial to write this as u to the negative second. Remember that negative exponents mean reciprocal. So u to the negative second is the same as 1 divided by u squared, because now we can just use the power rule. And the power rule says that to find the antiderivative of a u of like x to the n or something like that, you just add a power. So negative 2 plus 1 is negative 1. We added 1 to our exponent, and then we have to divide by that power, which is negative 1. All right, that's the power rule. And then again, plus c. And you say, phew, that was exhausting. Let's box our answer. Let's go home. I'm glad we survived. No, we're not done yet, guys. We're not done at all. What did we start off with? We had an integral with x's. What are you giving me? What are you giving me u's for? I don't know what u is. Well, I do, because I did the problem. If the problem gives you x's, your answer should have x's. If the problem says meters, your answer should have meters, okay? If I ask you, hey, Joe, tell me, Joe, how far do I have to go to get to the bathroom? You say 12. What? You mean 12 feet? 12 inches? 12 miles? How far away is the darn bathroom? I really got to pee. Okay? So answer the problem in a context that makes sense. We need x's. Okay, so now we got to start backtracking. What is u? U is the sine of theta. Okay, so let's replace it. This is, again, let's put the negative in front. This negative exponent means reciprocal. U is sine of theta. Okay, whew, much better, much better. Wait a minute, Joe. We still have theta. What was theta? We go back? Oh no, I don't know what theta is. I know that x is 4 tangent theta, right? X is 4 tangent theta, but I don't know what theta is. What is theta? Yeah, you're gonna have to solve for it, okay? All right, so there's 2 different ways of doing this. You can solve for theta, or you can do the easier task of solving for sine of theta. And you might say, sine of theta sounds harder than theta, but it's not. And this, if you remember your trig class, which if you had me, you know I love these problems. And in my trig class, I say, this is gonna be so fun when you get to this in Calc 2. And all my students go, you're lying. But it's true, okay? Right? We want sine of theta. So let's divide both sides by 4. We get x divided by 4 equals tangent of theta. You say, oh, that's not useful. It's not sine theta. Tangent sine over cosine. We could multiply both sides by cosine. But then we have thetas on both sides. We don't want that. What's another way of thinking about tangent? Tangent is sine of theta over cosine theta. That's not helpful here. But it's also opposite over adjacent. Let's draw a triangle. Everyone loves right triangles. It's trig time, okay? If this is our angle theta, come on, be theta-ier than that. This is opposite over adjacent. So what's the sine of theta, right? This is what we want. We want sine of theta. Well, sine of theta is just opposite. Oops, that did not circle. Opposite over hypotenuse. Well, what's the hypotenuse? Pythagorean Theorem, baby, is back. A squared plus b squared equals c squared. Or 4 squared plus x squared equals c squared. The hypotenuse, take the square root of both sides. The hypotenuse is going to be the square root of 16 plus x squared. And don't you dare cancel these. Square roots do not work across addition. This cannot be simplified. This c, this is as far as you can go. All right, so that's our hypotenuse, the square root of 16 plus x squared. So what is sine of theta? Opposite over hypotenuse. Opposite divided by hypotenuse. And actually, technically, we didn't want sine, we wanted cosecant, but that's fine. Last step equals negative 1 divided by sine. 1 divided by sine just means reciprocal of sine, which is opposite over hypotenuse. Reciprocate that. It's hypotenuse divided by opposite. So we get the square root of 16 plus x squared divided by 4, which gets totally cut off for you guys. Divided by 4. There we go. Let's see. Ah, yes. There we go. That's our answer. You know what? Let's box this in green. Be consistent. What a beautiful answer. What a beautiful answer. We start off with the integral of 1 divided by x squared times the square root of x squared plus 16 dx. And this is the antiderivative. And it's actually been a long time since I've taught this material. If you check your answer on trig subs, I remember that sometimes you get some weird stuff. Like if we take the derivative of this, we're going to get 1 divided by 2 times the square root of all this, which is good because there should be a square root of all this in the denominator. But then when you use the chain rule, you get a 2x on the top. We have an x squared on the bottom. We don't have a 2x on the top. So I don't really remember the relationship with that. And if I were actually teaching this class, I would have made sure to investigate that and remind myself before actually talking about it. But it has been a while since I've done it. But they can't be equivalent, I don't think. Unless maybe it's related to like an integration by parts step. That was optional. So we have another way of doing this. Oh, yeah, thank you. So it does check out. But the thing is, the denominator is not 4, right? We wanted sine. Sine is opposite over hypotenuse. I did adjacent over hypotenuse. So it will actually just be an x on the bottom, not a 4. Goodness, it has been a while. All right. So yeah, if you check your answer, you'll get the square root in the bottom, which is what we want. No, because, yeah, if you check your answer, you have to use the quotient rule. You know what? Let's check our answer. Let's not do hypotheticals. All right, let's check our answer. You guys are in for a treat. All right, so we have the negative square root of 16 plus x squared. This is going to really suck to check your answer. Oh, my word. No, it should just be x, I think. Hopefully. Check our answer. Check our answer. We need to differentiate that answer, which is negative square root of 16 plus x squared divided by x plus c. So to differentiate this, we need to use the quotient rule. Let's just bring the negative out in front. Okay. Quotient rule. Ooh, it's really been a long time since I used the quotient rule. Is low d high minus high d low, square the bottom, and away we go. So the derivative, or the bottom, so it's the bottom times the derivative of the top. Derivative of the top is going to be just 1 divided by 2 square root of 16 plus x squared times the chain rule, gets a 2x on top. I can make that a little prettier. That's low d high. Forgot the 1/16 that I took out at the beginning. Oh, wait, where did that go? You're right. Where did this guy go? It's when I changed the, good call. There's been a 1/16 everywhere here. When I changed the boards. I need to remember that for when I do this for my students. To watch out when I change between scenes. So it's going to be 16 on the bottom. 16 on the bottom like so. Good catch. Thank you, Alex. So there's going to be a 16 down here. So we're going to do a 1 over 16 out in front with a negative in front, and that should be fine. All right, so that's low d high minus high, which is the square root of 16 plus x squared times the derivative of the denominator. And actually, again, we took the negative 1/16 out in the front, so our denominator is just x, which is 1. And the denominator squared is x squared like so. Should be this. We're going to get an x squared on the first term. Hope this is right. So we get negative 1/16 times becomes 2x squared. Well, the 2's are going to cancel, right? It's going to become x squared divided by square root of 16 plus x squared. Minus, this is just the square root of 16 plus x squared. And the denominator is just x squared. Yeah, I'm getting nervous. What did I do? Negative 1/16 times the first thing, x squareds are going to cancel. 1 over square root of 16 plus x squared. Second thing, you have the square root of 16 plus x squared over x squared. This actually might be fine, right? Maybe not. Yeah, I definitely did something. Or no, maybe not, but maybe so. Let's not do this step actually. Let's do this step. Let's simplify this line a little differently. We don't want to split it up. And the reason why we don't want to split it up is that our end goal doesn't have it split up. The different way of simplifying the complex fraction here is multiplying by the LCD, which is the square root of 16 plus x squared. We do that on the top. We do that on the bottom. What happens is we get a negative 1/16 and times this fraction, which on the top, when we distribute, right? The thing on the left, they cancel. We're just left with an x squared. Thing on the right, it's itself times itself with a square root. They cancel. 16 plus x squared is what we're left with. On the bottom, what do we have? We have x squared times the square root of 16 plus x squared. We have a lot going on right here. But most notably, right, on the top, we have x squared minus x squared. Those cancel. The top, we have negative 16 only. The negative 16 is going to cancel with this negative 16. What are we left with? Phew. We're left with only a 1 on the top. And on the denominator, we have x squared times the square root of 16 plus x squared, which should have been our original integrand. It really has been a while since I've taught this. Thank you guys for being patient. So that should have been what we wanted. All right, this is all just checking our work. Original problem, the integrand was 1 over x squared times the square root of x squared plus 16. When we checked our answer, it checked out. Checks out. Cool. Smiley face. All right. We have done 2 integrals in 1 hour and 15 minutes. Oh, man. The joys of calculus. Yep, Fenula. I do indeed teach math. This is one of the things, by the way. So there's like a discussion at the college right now, at my college. Like, why do we have final exam sessions? Why don't we just have people take final exams during a normal class period? This is the problem. If your class period is 1 hour long, how the heck are you supposed to give a Calc 2 final exam? Are we going to put 2 problems on the final exam? Only 2 problems? Each problem worth 50% of the final exam? Like, oh man. We got to figure out something different to do. It's crazy. Oh, thanks, Alex.
I'll use my prime to celebrate.
Helping me catch the 16 and giving a prime sub. I appreciate that. Yeah, I teach at a 2-year college. Community college, depending on what you're familiar with. All right. Should we do one more problem for the... Is there a piece of calculus that anyone just really loves or really wants to talk about? Oh, thanks, Lamarck. I'm retired? No, this is my full-time job. Classes start next week, though. Related rates are pretty fun. We could do a related rates problem. Go back to Calc 1. L'Hopital's rule is kind of cool, too. You know what we're not doing? We're not doing partial fractions. I refuse to do partial fractions unless it is part of my job. Unless I'm teaching an actual class, I'm not doing a single partial fraction decomposition. Screw that. I'm doing all right. Thanks. Hey, Tashi-san. Going to Calc 1 next week? Awesome. Let's do a related rates problem. I love related rates. Related rates are cool. Let's find a good one. We got an image with a lighthouse. A lighthouse L on an island 4 miles away from the closest point P. If the lighthouse light rotates clockwise at a constant rate of 10 revolutions per minute, how fast does the beam of light move across the beach? 2 miles away. Oh yeah, this will be fun. I usually play like Brand or Vel'Koz or something like that. Okay, so let's look at this real quick before we go to the tablet. All right. So it's asking, so we have a lighthouse right here. And the land is 4 miles away. So let's say at some given point, the lighthouse is pointing the light directly down here. After a little bit of time, it's pointing the light over here. The question is, how fast does the beam of light move across the beach? So how fast is the beam moving when it's right here? Kind of what's going on. All right. I hate math, but I like you. That's the best thing I can hope for my students, for most of them. All right, so let's get into this. One more. Oops. Thing. So we got one more problem to do. And again, what do we've got? Got the situation. The lighthouse is on the top. This is a right angle. When this is 2 miles and this is 4 miles. That is the weirdest MI I've ever seen in my life. Okay, and what else do we have? We got, we included the 4 miles away. Okay, we included the 2 miles away. And the light rotates clockwise. Oh, so it's actually going to the left, not the right. Going clockwise. Oh, crap. When I do the clockwise motion, it looks counterclockwise to you. I have to go backwards, just like I'm teaching an actual class. It's going clockwise. So the light is going, oh, I drew it, but you can't see it. The light is rotating this direction at 10 revolutions, right? 10 revolutions per minute. The question is, how fast is the beam of light moving at 2 miles? So in this case, how fast is the beam of light moving? How fast? And any application problem you're doing, the most important thing is to get a good idea, a good picture. And I can't draw good pictures, but I do my best. Okay. Oops, I missed a 10 right here, 10 revolutions per minute. Okay. So for related rates, the most important situation, most important thing you can do, and there are some great step-by-step approaches out here. In fact, this book, I haven't checked this, this book probably has a really good, oh, look at this, problem-solving strategy, solving a related rates problem. Boom. So you could follow that, but I'm just going to talk to you guys because whatever. So keep getting cat hairs on my tablet. So we need to put all these things in terms of variables and equations. We got a right triangle here. Ooh, this sounds familiar. Sounds just like the trig subproblem we were doing, right triangle, trigonometry, Pythagorean theorem, right? A squared plus B squared is C squared, or X squared plus Y squared equals C squared. X squared plus Y squared equals Z squared. You can use whatever variables your little heart desires, okay? If you want your variable to be a squiggly thing, that can be a variable, okay? But I like using X's and Y's and Z's and Q's and R's and thetas and gammas and whatever. Do whatever you want. Okay. So what do we have? Let's say right here we have X squared plus Y squared equals Z squared. This is our Pythagorean theorem. So for a related rates problem, we care about a derivative. Okay. Derivative with respect to time. okay? And the whole idea of related rates, if you remember back to implicit differentiation, right? If we dx all this, right, then we're going to get a 2x right there, and that's it. Because the variable we're taking the derivative with respect to is the same as the variable here. But if we ddx this, it'll be 2y times y prime. Implicit differentiation. If we take the derivative of something that is itself a function of x, we have to use the chain rule, increase, and use implicit differentiation. Okay? And in this case, we're not even trying to find the rate of change with respect to x, right? We need how fast, miles per hour, meters per second. Okay? Fast is length per time. We need to see how is this changing related to time. Okay? Well, with respect to time, that's t. So, we don't have just one variable. We don't have just two variables. We don't even have three variables. We've got 4. It's your lucky day. All right? But it's not going to be as bad as all that. So let's use implicit differentiation and ddt the Pythagorean formula. Okay? So implicit differentiation on the x squared, it's going to be 2x, and x is not the same as t. So we need to use implicit differentiation, and we get dx dt. If you're lazy, you can write x prime. X prime, dx dt, they're both okay. Dx dt is more specific, so it's kind of better, but it doesn't have to. Acceleration is dv dt, exactly, yes. Because remember, this is acceleration, right? Not remember, I'm telling you this. Because, what do we got right here? See ya, real king. This is how fast does velocity change with respect to time. Velocity changing over time, that is the definition of acceleration, okay? So you can also remember, right, that acceleration is how fast velocity changes. Velocity is how fast position changes. So the second derivative of a position equation is also your acceleration. And there's a very nice derivative relationship between acceleration, velocity, and position. Okay, so let's continue with our implicit differentiation. All right. So for me, different people write their letters differently, even in the US. Some people write their X's like this, and it's really hard for me to communicate this because literally the reason I'm streaming right now is to practice drawing on my tablet because I need my handwriting to get better. Okay. Some people do X's like that, but I don't like that because a lot of times that looks like a cross product. What I like to do is I like to make my X's like a little curvier, kind of like that. And then my cross products are like smaller and supposed to be straight. But again, I am on my tablet. My handwriting is not that good. But usually people don't do... Oh, no, I misunderstood your question, Alex. X dot. I only saw that in graduate school. Actually, the X dot. And I don't even remember exactly what it looked like, to be honest. That was the first time I had ever seen it. You saw it in physics in undergrad. That's probably what it is then, because the person I saw it from in graduate school was a physics guy teaching our applied math graduate course. That's probably what it was. Anyway, so we got 2x times dx dt plus 2y dy dt equals the right-hand side 2z times dz dt. So there's a whole lot of stuff going over here. Okay. dx dt is instantaneous velocity. That is true. Specifically, the instantaneous velocity in the x direction. Right? So this right here is how fast the x is changing. And remember, I didn't label it like I should have. Remember that this over here is the x component. This distance here is a y component. This distance up here is a z component. I can write a z. All right. So this is going to look like a mess. Okay. Why do we even do this? Because we're asked about a rate of change. Okay. Remember, we are asked Ooh, we're not asked it here. We are asked somewhere to find out in number 39, how fast does the beam of light, how fast, immediately we know we need rates. How fast does the beam of light move across the beach? We need to know how fast is this x thing changing? So we need dx dt. And the only formula that we know about this triangle is the Pythagorean theorem. That's why we knew we had to start with this, but we needed dx dt. How do we get dx dt? We d dt both sides. Okay? So that's why we did this. And it might look like a bad idea, but again, at this point, you've probably seen a lot of related rates problems, so you kind of see where this is going. It looks like a mess, but it's really not that bad at all, because we're asking questions about this specific moment in time. Okay? So what do we know about this specific moment in time? We know that x is 2. Right here. We can plug that in. What is dx dt right now? Well, we don't know. That's literally what the problem is asking us to find. This is what we want to find. We could abbreviate want to find as WTF. Okay? That's what we want to find. I've actually haven't used that joke in a class for a long time, but I really want to do it next time I teach a calculus class. Might do that in the fall. All right. So what else do we know? We know at this particular moment in time, y is 4 miles. What is dy dt? Wait, hold up. I'm confusing myself. Dy dt is 0 because y is not changing. In this triangle, this distance is not moving, right? The only thing that's changing in the triangle is this distance because it's rotating, and this distance. Dy dt is 0, which means this term completely goes away. All right. But now I'm confusing myself. Good. We do know stuff about dz dt. That's the hardest thing, is dz dt. Before we go into the harder thing, let's find out what z is, okay? Z is our hypotenuse, right? And you might say, Jason, you didn't give us z. You only gave us 3 pieces of information, Jason. 4 miles, 2 miles, 10 rotations per minute. Or revolutions per minute. I erased that. But if you know 2 sides of a right triangle, you know the third side. Okay? So z is just going to be 2 squared plus 4 squared equals z squared. And you're going to get that. This is 4 plus 16 is 20. Z is the square root of 20. Just 2 root 5. Okay. And the final thing we need to know, you're not going to have room for this on your screen, is what is dz dt? And this is going to take a little bit more to work with. Because, right, what are the 3 pieces of informations? Y, X, and this guy over here. 10 revolutions per minute. Okay. I think we have to use that. So revolutions per minute. Actually, I think I'm using the wrong formula, honestly. I think we should be using a trig formula here. Should I not? Or was I correct in using the Pythagorean theorem? Because we can maybe convert that 10 revolutions per minute into some sort of speed. But that's like that has to do with like a change in theta. So it may have been better to use some sort of tangent function. Would it have? We did that, right? If we let this thing on the top be theta, if tangent of theta is equal to y over x, or sorry, x over y. Well, I did use the Pythagorean theorem. The question is finding the dz dt. I don't think that's trivial given this information that we have right here. Use 2 squared plus 4 squared equals z squared to find dz dt. Oh. That should work, right? What we have is this guy on the bottom. If we ddt both sides, what do we get? I'm actually going to move up. Right, the left-hand side is 0. The right-hand side, no, this doesn't work. 2z times dz dt. Because then you're just going to get that dz dt is 0, which is not true. You can't plug in only some things into the equation, I think. But if we did something like this, tangent of theta is equal to x over y, and then d dt this, would this be a, no, this might be a terrible idea, right? Then you get secant squared of theta, d theta, dt, equals, and you have to use quotient rule over here. Y times dx dt. Minus x times dy dt all over y squared. No, I think you have to do this. I think this is the way, yeah. I think this is the related rates equation that you use. Pretty sure. I haven't actually done a problem like this before. I just assumed it was a squared plus b squared equals c squared like we've done before, like I've done before. I've never taught a class has this in it before, which I feel like I'm saying a lot, and I feel like I'm full of excuses, but the way it is. Because then we can use the 10 revolutions per minute. We can convert that into radians per minute and get an effective unit, and we can get our stuff. So what that means is we're actually going to erase all of this. There's got to be a quicker way of erasing, I think. All right, so our guiding equation is actually not going to be the Pythagorean theorem. It's going to be trig. We have that tangent of theta is equal to opposite, which is x, over adjacent, which is y. We ddt both sides. Okay. And actually, hold on. What are we looking for? Let's use a little foresight. What are we looking for? We're trying to, right? What do we want to find? We want to find dx dt. So if we're solving for dx dt, let's just multiply both sides by y and get x is equal to y times the tangent of theta. That's going to make it so we don't have to use the quotient rule either, which is nice. All right. So let's go over here. Actually, the z is, no, we don't need the z. There we go. So let's ddt both sides now. What we're going to get is dx dt equals the product rule, which is y times secant squared of theta, d theta, dt, plus dy dt times tangent of theta. So, and now we can just plug things in. And again, what do we have? Just like before, right? dy dt is still 0. Right? dy dt, we found that out over here. It's still 0, which means this whole term goes to 0 as long as tangent is not pi over 2 plus pi k, which we can assume that in this situation. So really, all we have to look at is this first half of this equation over here. Theoretical physics? No, I don't know that stuff. Apparently, I don't even remember calculus. So what do we got over here? We need to plug things into this equation. So just like before, right? We were trying to find x, dx dt, y, dy dt. We need to find theta, and we need to find d theta dt. So the theta at this point, we can find that using trig. Okay, and again, we don't even care about theta really. What do we really care about? This is still, what was it, 2 root 5. Sorry, hypotenuse. We don't even care about theta. We care about secant squared of theta. So you could find theta if you wanted to, but we can kind of save ourselves a step and find out what secant of theta is, and then just square it. All right. So secant of theta is the reciprocal of cosine. And again, this is our theta right here. Cosine is adjacent over hypotenuse. So secant will be hypotenuse over adjacent, which is going to be 2 root 5 divided by 4. And again, that cancels to just root 5 over 2. That'll be secant of theta. Let's plug everything in. Go back to this equation. dx dt, that's what we want to find. So we got our dx dt equals y. What was our y? Our y was 4. So replace this y with 4. Secant squared, that's root 5 over 2 squared. Times d theta dt, which we haven't filled in yet. We'll leave that blank for now. All right. Yeah, exactly, Lamarck. So this comment right here is because dy dt is 0. Okay? Because what is y? Y is the distance from the lighthouse to the shore, and that is not changing. The lighthouse is not moving. The shore is not moving. We're talking in small time scale right now. Okay? So we still need to find d theta dt. Goodness, this is a nastier problem than I thought it was going to be. So we really have to use this final piece of information that we haven't used at all. 10 revolutions per minute. The theta is in radians or degrees. You can use either radians or degrees, but radians are going to be better almost all the time. Okay? Especially when you're dealing with, pretty much everywhere in calculus, you're always going to want to use radians. You can convert it to degrees at the very end if it matters to you, but we want radians. So we need to do a unit conversion, okay? We have 10 revolutions per minute, but I want radians. I don't want revolutions. So the question is, what's the relationship between revolutions and radians? Well, one revolution is 360 degrees, just 2 pi radians. All right, so that's our d theta dt. It's actually 20 pi. And again, the revolutions cancel and you get radians per minute. All right. Yeah, good, Lamarck. Good. So what do I do for work? I'll give you a hint. All right. So that's our d theta dt. It's just 20 pi radians per minute. Let's plug that in on the right-hand side. That's our dx dt. Let's simplify a little bit, right? We got 4 divided by 2 is 2, times 20 pi is 40 pi. We got 40 pi times the square root of 5. And what are our units in? This was radians per minute right here. What's the length of a radian? What's the length of a radius in a radian? Well, everything in here is in miles. Okay, this is going to be miles per minute. Miles per minute is not a very useful metric. I will accept it. on an exam, but really we should probably change this to miles per hour and get an approximation. What we're going to do is that's going to be equal to, well, let's not use approximately yet, right? That's going to be equal to 40 pi times the square root of 5 miles per minute. But 60 minutes are in 1 hour. To do that unit conversion, type that into a calculator. We don't multiply the 40 and the 5 because the 5's in the square root. So we can't bring something outside of the square root inside of the square root. We can't combine those unless they both have square roots. Okay. Assuming that's your question. So again, the minutes are going to cancel here, and then we'll have miles per hour, which is a decent unit. But what does Google say that is? 40 times pi times the square root of 5. And if you use degrees here, by the way, then you have a really annoying conversion to do here, but we used radians, so we're saved. 40 times pi times the square root of 5 times 60 divided by 1. Whoa, okay. Hold on, guys. We did something. What did I do? This is not the wrong answer. It does say squared. Thank you. Thank you. That might make it a little bit better. Yeah, this 2 got away from me right here. See that? That's going to be 5 over 4, which makes, I see. Thank you, Binomus. This is going to be a 10, and then square root of 5 squared is going to be 5. This is going to actually be 50 pi right here. Still think this doesn't fix my problem, because this is way too fast. Oh, you can't see it. Good call. It's still way too fast. What did I do? Right, 50 pi times 60. That's 9,000 miles an hour? I don't think so. Oh man, what did I do this time? First off, 10 revolutions a minute is already fast. Is that what the original problem said? Yeah, 10 revolutions per minute. And 4 and 2. That part's right too. Our equation is right. That's supposed to be an arrow. Tangent of theta is x over y. Good. d dt'd, we get dx dt equals y secant squared d theta dt. That's right. Plus dy dt tangent of theta. dy dt is going to be 0, so that term zeroes out. Y is definitely 4. Secant is root 5 over 2. No, secant is not root 5. Yeah, it is. And then it's squared. Let's move that squared a little closer. Maybe this is the right answer. That's 5/4. How did I get here? 5/4 times 4 is 5. 5 times 20 is 100. This should be 100, no? Not 50? No, my students don't want to do it with me. Or I don't want to do it with them. They're going to drop my ELO. My students suck. League. Yeah, right? I'm not crazy. This is 5/4 right here. 5/4 times 4 is definitely 5. then we get 5 times 20 pi. It should be 100. Arithmetic is too hard for me, yeah. And then really our units are in miles per minute, right? That's the problem, is their units. So fast. 10 revolutions a minute. It's a revolution every 6 seconds. No, this might be right actually. Right? If you think about a lighthouse, it could be right. What if we just check our answer, okay? What if we just check our answer? 100 pi times 60, right? That's 18,849.5 repeating miles per hour. Let's check our answer. What section are we on? 4.1. 100 pi miles a minute. That's what I had. It's just yeah, we were right. That's fast. It's fast. But I mean, if you think about it, right? If the lighthouse is rotating every 6 seconds, the light's going to be moving pretty fast. 18,000 miles an hour, though? That's really booking it. Okay. Huh. All right. There it is. Almost 19,000 miles per hour. Oh, and that's a good way to think about it, Alex. That's a good way of like instead of doing the right, we use related rates to find the exact horizontal change, but you could get a really good approximate rate of change by, instead of thinking about it as a triangle, you get an approximate by thinking about it as a circle, and the calculations are way easier. Good call, good call. That's exactly how fast your teammates run it down mid. Yeah. We must have the same teammates. Are you in my ELO? Yeah. All right, cool. So we did some good problems today. If you just joined us, you missed some good math. What did we start off with? We started off by doing some integrals. We did a double integration by parts problem, which was really cool. And then we checked our answer using the product rule. We got to use product rule here, got to use product rule here. It was good stuff. And look, we did get the original integral, and it did cancel out. Then we did a trig substitution problem, which was really cool. So we talked about trig identities and stuff like that. Did the sub, plugged it in. Get down here. Have to substitute more stuff, so we went to the next page and said, we already did a trig sub, let's do a u substitution as well. Does it get any more fun than that? And we finally, hey Rob, thanks for the raid. We finally evaluated the integral, but then this was u. So we had to say, okay, what is u? We had to plug that back in. So then we find what it is in theta, but that's no good. We need it in x's. So what did we do? We had to go through this long line of stuff to say, what is sine of theta? Well, we used what we knew about this from our substitution to find out what sine of theta is. We drew a triangle, found out what sine is, and replaced it. We got our answer here. And then we said, what's even more fun than doing this antiderivative? Let's check our answer with derivatives. Okay? So we checked our answer with the derivative. We went to the next page. Let's check our answer. What is the derivative of our final answer? And it should be the original integrand. Okay? So we used the chain rule coupled with the quotient rule. This is the quotient rule right here. Everyone's favorite rule. Everyone loves the quotient rule. And then we got to do some simplification, some really neat algebra right here by eliminating complex fractions, multiplying by the top and the bottom by the LCD. And then we got some really nice cancellation, and it checks out. How cool is that? And then the last thing that we did a related rates problem. This one really caused me some trouble because it was a related rates problem I hadn't seen before, and I had some incorrect expectations. I thought we were going to use the Pythagorean theorem as our basic equation that we differentiate in order to find the rates. But the Pythagorean theorem is the wrong call here because one of the pieces of information we got was a rotational velocity. And you can't easily use rotational velocity if you try to use Pythagorean theorem. How to use rotational velocity? You need some sort of trig function. So we eventually related the pieces of information that we had using this equation. And if I had recently taught a related rates lecture, I would have imprinted it upon the students and remembered myself that when you come up with this equation, the most important thing is that you come up with an equation that models the data that you have. What was the data that was given? A y, an x, and a rotational speed, okay? That was the big thing that I missed on the first attempt on this problem, okay? But once we got that, we just try not to screw up on algebra and just do a little bit of calculus, right? Everything that you know over here, plug it in to your stuff over here and get the right answer. Whew. We had a fun 2-hour math stream today. You could solve this last problem by calculating the hypotenuse and calculating directly the speed in that circumference, almost for sure. But I think it's not. I don't think that's a simple calculation, is it, Alex? Right? If we actually look at this, and again, I am more than willing to be wrong. Right? We have a triangle right here. The right triangle. This is 4. This is 2, and it's rotating at 10 revolutions per minute. I don't think it's trivial to figure out how fast this z is changing. Because essentially, don't you have to use trigonometry anyway to relate this rotational speed to the hypotenuse? The circumference is 2 pi z, yeah, but I don't see how that's useful. Like, even if we extend this to like a circle, (20z pi per minute). Hmm. (20z pi per minute's not the answer because z is 2√5. I think that's again just approximating. No? Because this z right here is getting shorter and shorter as time goes on. And then situations where you have some sort of like inscribed triangle are pretty messy to deal with. Right? It's really hard for me to draw dotted lines with a stylus. This is a radius. This is a radius. Like this thing is the thing that's changing. I don't know. You might be right, but I don't know how to do it. But either way, I really appreciate your comments. They have helped me greatly. Thank you. All right. So wait, how do I erase this? Oh, there we go. Excellent. So then something that I would do So the way that I'm planning on teaching this semester for my online class is doing a bunch of very small videos, each video like 5 to 10 minutes long. Each video only one or maybe two problems and a concept. And then one of the cool things is that you can very easily export this to a PDF, right? And then I can just, if they want the notes afterwards, instead of just watching the video, they can kind of look at it that way. That's cool. Thank you guys for being a soundboard. I am practicing writing on my tablet. I'm practicing doing math. It's fun to have people here. I might do some more math in Q. I'm streaming League tomorrow night. I might do some more math in Q. I might not. I'll have to do less heavy topics, right? You can't do this problem easily in a Q time, right? Problem takes too long. But we'll see. I still haven't figured out how to easily type in this region with my given tablet. I talked to my coworkers. There's a lot of ways to get around that, a lot of ways that they're getting around that. But I think with my current tablet, it's not feasible. I'll either have to get something else or just utilize some of the college's resources, which they have for checkout. Oof. Anyway. I think we're done. I have a Galaxy Tab S2. It's pretty old. It was old when I got it. I got it a while ago. When it was, it's not super old, 5 years. 5 years old isn't super, 5 years old is kind of low. I don't know. It's too old to have the technology. So a lot of newer tablets have what's called like, I think it's called a palm rejection or something like that. Yeah, Lamarck, it was nice having you here. See if we do this again. All right, I think that's everything I'm going to talk about. I had a lot of fun today. Thank you guys. This was neat. See you later.